The James Webb Telescope has shown us that there are many problems with current cosmology. Other models would seem to be a much better fit with the images we see, but cosmologists refuse to let go of their old paradigms. Let's explore some of the old and new data from James Webb and understand the problems this creates for their model, and then look at how other models explain it in a different way. In the standard model, the universe was formed in the Big Bang. From this, stars formed, which then eventually grouped together to form galaxies. The early galaxies would then grow larger through mergers and collisions to create the galaxies we see today. This would mean that as we peer back into the early universe, the number of galaxies should decrease, and we should see less and less spiral galaxies. In this model, there is a period called the cosmic hydrogen reionization period. This period is thought to be responsible for converting a large amount of neutral hydrogen back into its plasma state. This, they claim, occurred about 150 million to 1 billion years after the Big Bang. Images from the Hubble Space Telescope seem to suggest that the number density of galaxies sharply decreases as the redshift increases. This seemed to match very well with the idea that cosmic hydrogen reionization ended around a redshift of Z equals 6.2. This, they also claimed, is backed up by the detection of the 21 cm hydrogen-1 absorption of the cosmic background radiation. This would seem to indicate that the first stars came into existence at around a redshift of Z equals 17.2, placing this as the possible starting point for reionization. Even prior to the James Webb Telescope, a collection of galaxies had been identified which seemed to undermine this understanding of cosmic hydrogen reionization. In 2012, scientists detected an oxygen 3 line in a galaxy MACS 1149 JD1, which was at a redshift of 9.1. The very existence of oxygen means that the galaxy had already been polluted by the previous generation of stars. The authors of the paper concluded that the only way this was possible was that the galaxy must have formed at least 300 million years earlier, placing its redshift at 15. This would mean that the first stars would have formed at an even earlier time, pushing back the start of reionization. Finding these galaxies is also inconsistent with the idea that the number of galaxies diminishes at a redshift above 10, as this implies that reionization could not have happened. Hubble had its upper limit of detection at around a redshift of 11. The task of exploring even higher redshift objects was taken over by the James Webb Telescope. The initial release of data caused a worldwide stir, as it revealed a universe that seemed to show that the further back we looked, the more galaxies we saw. It showed that normal disk galaxy structure existed much earlier than previously thought, that mergers were not as common as thought, and that some galaxies have remained unchanged for over 10 billion years. Some then seemed to suggest that maybe there was a problem with the calibration of the telescope, or possibly that we were identifying objects that were giving false positives. So several months have passed, so has the view changed? A new study examined objects with a redshift between 11 and 20 from the James Webb Telescope data. They were able to detect these across multiple bands. This would imply that they are unlikely to be fake sources and are far away enough from what are considered contaminated regions due to mid-redshift old galaxies and brown dwarfs. They identified 86 galaxies that are at extreme high redshifts. Some of these, based on their redshift data, date back to around 13.6 billion years. These would therefore be some of the earliest galaxies that have ever been discovered. This would mean that they formed just 200 million years after the Big Bang. These should be extremely rare, but as the initial reviews seem to suggest, there appears to be far more well-formed galaxies right at the beginning of the universe. Worse is that the original idea is that these original galaxies start out as small and through mergers and collisions grow larger and larger. So they had expected to find that as they peered further back in time, they would see more mangled galaxies, but instead they see galaxies with smooth disks and neat spiral forms. In a different study, they examined red spiral galaxies which were in the initial batch of images released by the James Webb Telescope. These were thought to be very rare. In this image, they were able to identify one unusual galaxy which was passive, meaning it appeared to not be forming stars. This is a surprise since they expected galaxies in the early universe to be actively birthing stars. These raise big questions about their model of galaxy evolution. There are many problems that were identified in the original set of data released by the James Webb Telescope, and it would appear that these are not going away. So what are we seeing in the data? As the James Webb Space Telescope peers deeper, it is revealing smaller and smaller galaxies. There appears to be no hint of objects looking larger as redshift increases due to the expansion of the universe. If spiral galaxies are common in what they consider to be the early universe, it destroys the idea that galaxies evolve through mergers. We have galaxies that formed a mere 200 million years after the Big Bang. Analysis of the light from other early forming galaxies that date to around 400 million years after the Big Bang seem to indicate that they have stellar populations that are over 1 billion years old. The cosmological redshift we see may in fact be caused by other mechanisms. Both Halton Arp and Wal Thornhill believe that the majority of the redshift we see is due to an intrinsic process, which is related to the age of the object. Younger objects are more redshifted, and as they age they slowly shift to the blue end, meaning objects that are older than we are appear blue shifted. So Andromeda is blue shifted because it is older than we are, not because it is moving towards us. So when we examine the James Webb images, we see smaller and smaller, more redshifted galaxies. This could therefore be interpreted as smaller, younger galaxies. These would have originated from a parent galaxy, which would sit at a lower redshift. If the universe did not begin in a Big Bang, we have no expansion, and it is likely infinite. Halton Arp believed that the universe may well be made up of pockets of matter that form with vast distances between these pockets. He felt it was likely that we would only be seeing the material inside our own pocket. The fact that we see more spiral galaxies at higher redshifts and far less galaxy mergers shows that galaxies do not evolve into this shape through mergers and collisions, but that instead this appears to be a normal, default configuration that galaxies tend towards after a period of time. Another way to look at this is to consider that the cosmological redshift we observe is caused by the material the photons pass through. Now, in the Big Bang model, this is assumed to be caused by the expansion of space, but there are several alternative concepts that assume that the photons somehow loses energy as it travels through space, causing it to become more redshifted. Eric Lerner is a proponent of the tired light model, meaning that what we are seeing in the James Webb Telescope image is an infinite universe with galaxies extending out forever. As the light from more distant galaxies has more space to travel through, it becomes more redshifted. This means that there is a limit beyond which we can no longer observe the distant galaxies. Whichever of these two models you prefer, both fit the data far better than the current Big Bang model does.